Stoichiometry is the study of the quantitative relationships between the reactants and products in a chemical reaction. We use stoichiometry to be able to determine what quantities of reactants we need for a given chemical reaction, as well as to predict how much product we can form in a chemical reaction. The amount of product that we can determine is the theoretical amount and does not take into account experimental error. Now, in general, just as a reminder, we can represent reactions with this kind of image as you see. When we do a representation like this, we are drawing molecules and we are symbolizing a chemical reaction by considering that when we say 2H2 plus O2, we are talking about two molecules of hydrogen gas plus one molecule of oxygen gas that transforms and give two molecules of water. However, when we're doing calculations, we generally refer to quantities that are moles, not single molecules. That is because in a chemical reaction, there's a lot of molecules involved, and so making calculations with moles is far easier. In this lecture, we're going to use molecules to represent and understand the concepts, but for the calculations, we're going to use moles. For example, when we look at the reaction represented here of the decomposition of hydrogen peroxide to give oxygen and water, we can simply count the number of molecules that react to fill in those stoichiometric coefficients. And we can see that the balanced chemical reaction will be given by two molecules of hydrogen peroxide to give one molecule of oxygen and two molecules of water. The same reasoning can be used, and the same equation can be used to represent a reaction with more molecules or more moles. Now, when we do this, we can notice that if we divide all the coefficients that we obtain in this reaction by 3, we can obtain the original chemical equation, which is the one written with the smallest coefficients. And these substantially let us know that when we have a chemical reaction, we can use the ratio of the coefficients that we see to represent any number of moles that do react. So we're seeing that we can use the stoichiometric coefficients that appear in the chemical equation because they provide the number of moles that react to identify the number of moles needed of reactants and the number of moles produced of product. To work numerically with these quantities, what we can do is use the stoichiometric coefficients to write conversion factors. And these conversion factors can be used in dimensional analysis to determine exact quantities. So, for example, in the reaction of carbon monoxide with oxygen to produce carbon dioxide, we can write three conversion factors, which are ratio of moles, between carbon monoxide and carbon dioxide, between moles of oxygen and moles of CO2, and between moles of carbon monoxide and moles of oxygen. And we can use these for any calculations. So say, for example, we want to react 3.82 moles of carbon monoxide to form carbon dioxide. We can, by using a conversion factor, calculate the moles of CO2 produced. And of the conversion factors that we worked before, we're going to use the one that converts moles of carbon monoxide into moles of carbon dioxide, as you can see there. So we multiply our initial 3.82 moles of CO by our conversion factor and obtain our result as 3.82 moles of CO2. We can also calculate the number of moles needed of oxygen for this reaction by using the conversion factor that allows us to transform the moles of CO into moles of oxygen. And in this case, we obtain 1.91 moles of oxygen needed. So let's look at the practical example. So typical question can be, how many moles of HBr, hydrobromic acid, can form when we react 0.327 moles of sodium bromide. When looking at this reaction, we can write from these stoichiometric coefficients the conversion factors that we need to solve our problem. So in this case, we want to convert 0.327 mole of an ABr into moles of HBr. So what we want to have is write the conversion factor that relates the moles of HBr, which are the ones that we want. So there will be 3 mole of HBr, and have as a denominator the moles of NABr, which are the quantity that we want to cancel out, which would be 3 mole of NABr. And we can see that these quantities cancel out, and our result will be 0.327 mole of HBr. Now, we can also, if we wanted to, determine how many moles of H3PO4 we need for the reaction. So we simply write 0.327 mole of NABr. And in this case, because we want the moles of H3PO4, we will write 1 mole of H3PO4 divided 3 mole of NABr. So you can see that in the conversion factor, the numbers that are used are the ones that appear in the chemical reaction. In general, we do not have moles available when we work in a lab, but we do have masses. So what we want to keep in mind is that there is a relationship that is very well known between the masses and the moles. So once we have the masses, we can convert them into moles and then use the mole relationship from the chemical equation, as we've seen before, to convert the mole of one chemical into the moles of another and then convert back into a mass. So in general, what we use is what is called the mole map. So for a general reaction, we have the mass of a chemical A. We're going to transform that into moles of the chemical A by dividing by the molar mass. Then we're going to use conversion factors, as we have written before, between moles for chemical A to chemical B, and then we can multiply back by the molar mass of B to obtain the mass of B. Let us look at an example of how to apply this. So suppose we have the reaction we were looking at before between carbon monoxide and oxygen to produce carbon dioxide. Suppose that we have that 4 grams of carbon monoxide react, and we want to calculate the mass of CO2 produced and the mass of oxygen consumed in this reaction or needed for the reaction. Now, what we need to do, first of all, is convert the mass that we had original into moles, because we don't have a relationship in the chemical equation between the masses, but only between the moles. So we need to work in moles. So the first thing we're going to do is convert the 4 grams of CO into moles of CO. And then we can convert the moles of CO into moles of CO2 using the conversion factor 1 mole of CO2 to 1 mole of CO, or 2 moles of CO2 to moles of CO. Now you see how, and this is something that I wanted to show you here, sometimes the conversion factor do not use the exact numbers that you see in the chemical equation. You may see examples where you see that these conversion factor are already divided, and so the conversion factor is the same. So you can write it as 2 mole of CO2 to 2 moles of CO, or 1 mole CO2, 2 moles of CO. And at this point, once we obtain the moles of CO2 with this conversion factor, we can convert that into a mass by multiplying by the molar mass of CO2. Now, we can apply the same reasoning and the same technique to obtain the moles of oxygen needed for the reaction. So in this case, our conversion factor is 1 mole of O2 2 moles of CO. So the moles of CO that we have calculated before, we're going to convert into moles of O2. And then by multiplying by the molar mass of O2, we're going to obtain the grams of O2. Let's look at one more example and let's see how we can do it step by step. So how many grams of ammonia can be produced by the reaction of 14.75 grams of N2, and how many grams of H2 are needed for the reaction? So I'm going to pass to my notepad, and we have the reaction here, and we have our data that we need to solve. So the first question is, how many grams of NH3 can we produce? So before we can answer that, we cannot go from grams to grams. So the first thing we need to do is transform these into moles. So we're going to take our 14.72 grams of N2, and using the molar mass, so 28.02 gram per 1 mole of N2, we're going to transform that into moles of N2, and we're going to get 0.5264 mole of N2. Then we have the moles of N2. We want to transform those into moles of NH3. So our conversion factor is, there are 2 moles of NH3 every 1 mole of N2. So we can get our 0.526 mole of N2 and multiply that by our conversion factor, that is 2 mole of NH3 divided by 1 mole of N2. And this is going to give us 1.053 mole of NH3. And then we can get the grams of NH3 by multiplying the moles, so 1.053 mole of NH3 multiplied by the molar mass of NH3, 17.03 grams per 1 mole of NH3. And we get 17.93 grams of NH3. So you see how this is obtained. So it's grams to moles, then moles to moles, and then moles to grams. You have to always make sure that when you have the moles of a species, the molar mass is that of that species when you multiply or divide. Now, let's look at the second question, that was if we have the same amount of N2, so we had our 0.5264 mole of N2. We already calculated that. We want to convert these into moles of hydrogen. So we're going to first convert, because we want to determine how much hydrogen we need for the reaction. 1 mole of N2 for 3 mole of H2, and this gives us 1.579 mole of H2. And then we want to convert the 1.579 mole of H2 into grams of H2, which means we're going to multiply by the molar mass, 2.020 grams per 1 mole of H2, and we're going to get 3.158 grams of H2.